Hello, and I'd like to show you and share with you a worked out problem from the textbook from chapter 5. I found this to be a pretty tough problem to work on, and so that's why I selected it to uh, show you all how to work on, I think, what I would consider a tough problem. So let's go ahead and get started. I'd like to show you at least my solution of worked out solution of problem 551 in your textbook. So I'm going to read you the problem statement. You can read along, and then we will go about solving the problem by dissecting the words there, keywords, start with a sketch, and then move along to think about how will I solve this difficult problem. Here we go. An ideal gas within a piston and cylinder, it executes a Carnot power cycle. That's key, Carnot power cycle. Shown in figure 513, we'll go get that screenshot. The isothermal compression process occurs at 300 K from a pressure of 90 kPa to 120 kPa. Okay. It says the thermal efficiency is 60%. Determine two things: the temperature of the isothermal expansion, whatever that means in degrees K, and B, the net work developed in kilojoules per kilomole of gas. Oh, okay. For me, this kilojoules per kilomole throws me for a loop, I got to tell you. All right, let's look for some key words here. Let's look for key words in the problem statement. Ideal gas. Immediately in my mind, as a problem solver, as an engineer, the ideal gas equation of state comes to my mind. P times little v equals RT, and all of the related identities associated with that, with the N and the R bar in it, that type of stuff. Piston and cylinder, okay, closed system. I write that down. If this were a quiz, I'd write that down, okay? That's going to be powerful for us when we write the first law of thermodynamics. Executes a Carnot power cycle. Now, in my mind, I remember that's 4 special processes. Sometimes I have to remind myself of what are those 4 special processes. That's why we're going to get a screenshot of figure 513 to refresh our memory on what are those 4 special processes. One of those is an isothermal compression occurring at a given temperature, okay? Thermal efficiency given, for me, that says, look, that's going to be a key in solving this problem. Somehow the thermal efficiency given is going to be a key, okay? And then part B, which I dread, okay, net work developed in kilojoules per kilomole. And I refresh my memory, that's W net, little W net bar, which I dread working in, and that's equal to capital W net, the net work in joules or kilojoules, divided by N, the number of kilomoles, kilojoules per kilomole. Okay, so that's the setup. We've picked out the key words. Before we draw our sketch, let's get a roadmap of where we're going. This is a tough problem that I would say a tough problem for undergraduate level, very tough undergraduate level problem, very reasonable at the graduate level, would take some difficulty, but very reasonable for graduate level. We're going to write down what we want, at least for my purposes, remind myself, what do I want to find in this problem in the first place? Then what is given? What kind of specific things are given in the problem? We'll talk about what are some immediate roadblocks that I had when I was solving the problem. We will start with a sketch, which we must see, and we will discover from the sketch that part A is easy. We will also discover that part B is going to be tough, and we're going to get through those steps. And I got stuck over and over again on this problem, and I reminded myself, my own guidance that I give students that I got from my professors: when you get stuck, write down the first law of thermodynamics. And I wrote down the first law of thermo for each of the 4 processes, and that's what delivered me to the promised land. So Then we'll methodically solve part B once we do that. Okay, so part A, we're going to write down what are we looking to do. Temperature of the isothermal expansion. We're going to look at the sketch, and the translation of that is find T sub H. That's easy. Okay, if you have thermal efficiency and you have TL, finding TH is easy. Okay, then part B, find the net work developed in kilojoules per kilomole. That's going to be tough. That's little w net bar, which is W net kilojoules divided by N, the number of kilomoles. Okay, so that's what we're looking for in the tough part B. Okay, so let's see what's given. Ideal gas, that gives us the equation of state, ideal gas equation of state. We're given that we have a closed system. The Carnot power cycle, that gives us 4 very special reversible processes. So that's defined. The 4 processes are fully defined. Okay. We're also given isothermal compression, and we're going to look at the PV diagram to see that what that discloses is that T sub L is 300 K. And then thermal efficiency of 60%. We know that that's going to be a key in solving this problem, parts A and B. Okay, roadblocks. And so here's a roadblock that I had when I was solving the problem. I don't know if you got stuck or you sailed through it, but here was a roadblock I had. We were given an ideal gas, but we weren't exactly given the substance ideal gas. We were not given air or nitrogen or oxygen. And also, we were not given the number of moles. So we're trying to find the network developed in kilojoules per kilomole. Oh, and I hate those problems where you're not given either the mass or the number of moles. But I've got to solve this problem. Let's say I'm taking a quiz, or I've got to turn in my homework. I've got to keep moving whether I like it or not. Don't know the number of moles. We don't know the molecular weight. We don't know the substance, so we don't even know the molecular weight of the substance. And so therefore, we don't know the substance specifically other than ideal gas, so we don't know whether to model the specific heat, C sub V or C sub P, as a constant number or a variable number. We don't know. Okay, so those were roadblocks for me. Well, okay, so much for the roadblocks, but let's get started. Let's start with the sketch. The equipment and the high-level cycle schematic. These are musts that you've got to have shown. Okay, well, I showed the piston and cylinder, depicted closed system. That's good enough. All right. Then my high-level cycle schematic, black box. I labeled it Carnot to remind myself that the thermal efficiency is given, and for the Carnot cycle, right out of my mind, top of my head, oh yeah, that's a special cycle that reduces, thermal efficiency reduces to TH minus TL over TH. So if I know TL, then it's going to be easy to find TH. Okay, and then here are my heat transfers, QH bar, which is QH over number of moles, QL bar, QL over number of moles, and W net bar, which is W net over N. Another thing I did, let's say in my solution, is I immediately wrote down R bar. I know I'm going to have to use R bar, so I refreshed my memory. I know that by heart, and I hope you do too, what R bar is. At least you got to be able to go find it in your textbook. All right, so let's start. So in terms of starting with the sketch, we must draw the pressure volume diagram. I drew that with pencil and paper when I did this by hand, but here's the screenshot of the Carnot cycle taken right from your textbook. So let's have a look at this. Let's look at the details, and that's going to help us plan for our homework solution. Okay. First, the isothermal, part A, the temperature of the isothermal expansion. Well, the isothermal expansion is process 2 to 3. Okay. Isothermal expansion. So notice here that in the sketch that you could look in right out of your book, here's TH. Isothermal. See, that's a constant temperature line. It's not a straight line, it's a curved line, but look, it's labeled TH. So this is the temperature we're seeking, TH. Okay. Another thing in the problem statement, it said the isothermal compression. Well, here's the isothermal compression line, and it's labeled T sub C. In my world, that's T sub L, T low for me, T cold for the textbook. So in my world, TL is given in the problem. T4 equals T1 equals T low equals 300K. So with me jabbering along, you've probably already figured out, I immediately see how to do part A now. Okay. But let's keep studying because we're gonna have to do part B. Observe that the shaded area bounded by these four special processes is the net work. How do you know that? Remember the second week of class, you were in closed system, quasi-equilibrium process. We now call that a reversible process. Quasi-equilibrium, reversible. Okay, so for any closed system process, quasi-equilibrium or reversible, work is the integral of PDV. Work is the integral of PDV. And so let's start here, 1 to 2. What's the work done from 1 to 2? Area under the curve. Will it be positive or negative? Negative. We're integrating right to left. So it's I've written that down. Okay. Process 2 to 3. What will the work be? Integral PDV. It'd be a positive number, area under the curve. 3 to 4. What will the work be? 3 to 4. A positive number, integrating left to right. 4 to 1, that isothermal compression. It's negative. Work is negative. Integral PDV negative, integrating right to left. And so if you could do the math and get numbers for all four of those, add them together to get the net work. The shaded area is the net work. So you have a vision of part B. That's what you're driving at for part B. The shaded area, you're trying to get a number for that in kilojoules per kilomole. Okay. Another observation, and then we're going to move on. I may be putting you to sleep. Let's see. Let's look at process 1 to 2. That's called reversible adiabatic compression. Reversible adiabatic compression. Keyword, adiabatic. I've written down Q from 1 to 2 is 0. Process 3 to 4, reversible adiabatic expansion. Volume getting bigger, pressure getting lower. Adiabatic. Q from 3 to 4 is 0. So those are some key observations that the purpose of your working on this problem is to gain that knowledge, to gain that understanding of how to study and plan your work. All right, so we're moving ahead. Okay, part A, did I convince you that the temperature of the isothermal expansion is basically saying, what is TH? Translation. We've learned the temperature of the isothermal expansion is determined TH. Okay, and so this part's easy, right? The Carnot thermal efficiency is 60%. You remember from the top of your head that for the Carnot cycle, the thermal efficiency can be described by TH minus TL over TH. We looked at our sketch to observe that TL was 300K. You've got one equation and one unknown. Solve for TH, 750 degrees K. Okay, great. You've done part A. If this were a quiz, you're going to get a 50 at least. That's a lot better than a 0, right? It's a million times better than a 0. You've gotten good partial credit by getting this far. But let's go for the 100. Let's go for the full credit. Part B, much harder. All right. How do we start part B? Well, let's write down what we're looking for. We're looking for W net bar as described in the problem. Well, that's W net divided by N. Okay. And what's that made of? It's made up of the work added together for each of the four processes. So I've written this down on my paper. That's worth some partial credit. Okay. Be a little partial credit on part B. I also wrote down whether these work terms are going to be bigger than 0 or less than 0 with my eye. I don't know what the numbers are, but the work from 1 to 2 is going to be a negative number, 2 to 3, a positive number, 3 to 4, a positive number, and 4 to 1, a negative number. So I wrote those down too, praying maybe I'll get a little more partial credit for that, but I'm not going to give up. Okay. Next step. What do I work on first? I've got 4 terms to work on. I'm going to have to study my PV diagram. And when I got to tell you that when I was solving the problem myself, this was not obvious to me. And I've solved a lot of thermo problems. I studied my sketch. I studied, well, what's my given information? On my hand-drawn sketch, I'd scratched down some stuff that was given, maybe with some check marks, and studied on it. And I observed that we can find the work from 4 to 1 using W, the work, kilojoules, equals the integral of PdV from state 4 to state 1. I observed that. Now, you say, well, good golly, okay, he said that. Let's see, let's go through my thinking process, maybe to help you do the same. Here's a rehash of the pressure volume diagram for our Carnot cycle. Okay, process 4 to 1 is reversible and isothermal with an ideal gas. So I wrote this down. PV equals NR bar T, ideal gas equation of state. Okay. Can I write down the process path? P is a function of V. P is a function of V. I can. P is equal to NR bar T divided by V. Look at that, isothermal. Isothermal, constant temperature. And so T for process 4 to 1 is TL, okay? So P is NRTL divided by V, okay? Wow, that is, when I study, what is that math? The path is a classic hyperbola. N, constant, R bar, constant. T for this process, constant. V, variable. Easy to integrate. Okay, another thing I observed. V1 is N R bar TL over P1, and V4 is N R bar TL over P4. Now, when I was solving, I said, damn, I don't have N. Shoot, I'm stuck again. I had to do some more thinking and say, well, how can I get rid of N ratios? And so I can write down that, and I wrote this down on my handwritten part. P1 over P4 exactly equals V4 over V1. And we're given P1 and P4. So I started getting, my confidence level went up. That's our signal to use. The work from 4 to 1 is the integral of PdV from 4 to 1. That's where we're going to head. So conclusion, we studied the PV diagram. The only place I saw to start was process 4 to 1. So I did. And then I figured once I get through that, maybe I'll keep thinking. I won't give up. Okay, let's see where we wrote down the definition of net work. We studied our PV diagram to see that we can start with the work bar from 4 to 1. We'll do that. Okay. I repeated the observations is that we have the process path. P is N R bar TL over V. Okay. And then we've got those ratios that I came up with. All right. So now let's do the work of integrating PdV. Work from 4 to 1 kilojoules is the integral of PdV from 4 to 1. All right. So let's do the math. Let's put in our process path for P. We're substituting this glob for P. That's N R bar TL over V for process 4 to 1, TL, process 4 to 1, dV. I'll pull all my constants out of the integral. I integrate dV divided by V, 1 over V dV. That's the natural log of V from 4 to 1. Okay, so we've got natural log of V1 over V4. Okay, I don't have V1 over V4, but I do have P4 over P1. And I just discovered that ratio. I was feeling a little better about myself now. Okay, I'm getting somewhere. So the work from 4 to 1 is R bar known, TL given, natural log P1 over P4, both given. So we've got a number for W bar from 4 to 1 is negative 717.5 kilojoules per kilomole. We are getting somewhere. We're a fourth of the way there on W net. Yay. we'd get some decent partial credit if we got this far. Okay. Next step, tough step, one that requires a lot of thinking and studying the PV diagram and understanding the fundamentals of thermodynamics. Okay. Let's look at process 1 to 2 and 3 to 4 sort of together. Both of those are reversible and adiabatic processes. Boy, I forgot that. I forgot to have that in my head. Finally, I remembered it. So I'm going to write down Q from 1 to 2 is 0 and Q from 3 to 4 is 0. I wrote that down on my pencil and paper solution. I then wrote down the first law for a closed system for each process. Here we are. Q from 1 to 2 minus W from 1 to 2 equals U2 minus U1, process 1 to 2. And for 3 to 4, Q from 3 to 4 minus the work from 3 to 4 is U4 minus U3. I'm getting somewhere because I can, those terms are 0. So solve for W from 1 to 2. It's U1 minus U2. See, minus sign. I had to get my minus sign straightened out. Okay. And so the work from 3 to 4 is U3 minus U4. Okay. Now, another thing came to me. Okay. Not given. Nobody instructed me to do it. Wait a minute. I know I've got an ideal gas. I can calculate the change in internal energy for any ideal gas. Delta U is the integral of N, number of moles, CV bar dt. Now, I don't know what CV bar is, okay, but let's keep plugging along. I can calculate delta U. Man, I don't have N, but let me just keep writing stuff down. Okay, so here I've got the work from 1 to 2 is U1 minus U2. Here it is. Okay, there's the expression for delta U. And the work from 3 to 4 is N. Here's the expression for delta U from 3 to 4. Okay, wow. Now, what? Okay, T1 to T2. Wow, this is, T1 is TL. Okay, and T2 is TH. So really, I know T1 and T2, TL and TH. I've got both of those. Let's look over here. T3 is TH and T4 is TL. Wow. Well, let me just kind of write down the work from 1 to 2 in terms of TH and TL. Okay. I divided by N, and it looks like I need to put a bar over top of my little W's. Looks like I missed that. Sorry about that. You see how I've divided both sides here by N, and I missed putting a bar on top of that. Sorry. Okay. But observe, look at this integral. I don't even have to integrate it. I can see that the work from 1 to 2 exactly equals the negative of the work from 3 to 4. Look at the limits on the integral. Limits on the integral. If I flip them, okay, so that's the big conclusion, the big observation that is subtle but important. The work from 1 to 2 and the work from 3 to 4 in kilojoules per kilomole, they cancel each other in the net work expression. Wow. All of a sudden now I've gotten 3 out of my 4 net works, little works done. Okay, look at this. So now back to the definition of where we were. I've got these two are canceling each other. Those numerically equal each other exactly, except in the negative. They cancel. Wonderful. We are, boy, it's easy to forget. Where are we at? Where are we at? We found W from 4 to 1. We've got a number for this, okay? We're looking for this. All we have left to do is figure out W from 2 to 3 bar, okay? Okay, now where do we go? So, man, and so I went back to my PV diagram. I studied on it. I said, man, I'm having a rough time see how to get that. Well, so what do I know? What kind of stuff is given to me in the problem? What else can I write down? Whoops. What I wrote down was the expression for thermal efficiency. Thermal efficiency is 0.6, which is W net bar, don't have it yet, divided by QH bar. Don't have it. Now, I had to keep thinking, gosh, this is rough. Okay, well, what's QH? What is QH bar? Well, that's Q from 2 to 3. So let's look. Here's the reprise of the screenshot, 2 to 3. QH is Q from 2 to 3. Okay. And then I thought about the first law. Boy, it's like when you're stuck, think about the first law. Write down the first law or think about the first law. I refreshed my memory in my handwritten solution. Well, Q from 2 to 3 exactly equals the work from 2 to 3 because it was an ideal gas isothermal process. Wow, delta U was 0. So I can substitute in the denominator for thermal efficiency the work from 2 to 3. Oh, I can't tell you how happy I was when I when I got to this point. I said, man, this is great. I've got one equation and one unknown, right? Look at this. Thermal efficiency is 0.6. The work from 4 to 1, I've got a number for. Work from 2 to 3 is the only unknown. I can now get my number and I can be done with this problem. And here, I took a little screenshot from my a little piece of my handwritten solution and enhanced it here a little bit. And so you can see in my handwritten work, I said, okay, look, I've got one equation and one unknown in terms of the original variables, okay, instead of the number for work from 4 to 1, down to one equation, one unknown, serve for W 2 to 3. And so here we go. And so in my numerical work, calculator work, which I do in Excel, you can see that I've got a numerical value for W bar from 2 to 3 is 1793.8 kilojoules per kilomole. All that's left is to add these two numerical values together to get 1076.3 kilojoules per kilomole net work W bar. And that's part B. And I got to tell you, I was happy to get to the end of the problem. But I was kind of proud that I didn't give up. I didn't call the professor up and say, hey, professor, you're a lot younger than I am. All the professors are younger than me. Hey, I know you're a lot younger than me, but I cannot figure out how to solve this problem. Can you give me some guidance? Can I come to your office hours and get some guidance? I was pretty proud that I got to the end of this one on my own. So look, do not feel horrible if you had trouble starting this problem and getting to an end point. You should be very proud. If you didn't get any help at all and you got to the end of the problem, you should be very proud of yourself just starting out as an engineer. But I did want to give you this step-by-step, give you the step-by-step solution to illustrate that not all the problems are easy. It requires some hard work. Not all problems in thermo are this tough, okay? But this was a tough one. So I appreciate you going through the video with me, following the steps I did. I hope if you're still working on this problem, go back, pause, and kind of copy down with your hands what you're seeing on the screen and drive towards a final solution. But look, this was a tremendous, on the positive side, tremendous problem for you to learn more and more and more about putting all the thermodynamic fundamentals together to solve a tough problem. So thank you for watching, and I hope to see you again soon.